Sometimes my video making process is just downright comical. I've tried making this video like 5 times and something keeps happening. And then I finally made it, but the video was like 25 minutes long and I was like, that's ridiculous. So here we are again. Okay. So for topic 5, we need to talk about domain and range of trigonometric functions. And it is rare for me in the classroom to be like, just trust me, okay? This is one of those situations where, in some ways, I wish we didn't even cover domain and range at this point because once we see the actual graphs of the trigonometric functions, the domain and range is going to make a whole lot more sense. But we've introduced the idea of the unit circle, and we have a pretty good understanding of what some of the domain and range values should be. So we typically introduce it at this point in a trigonometry class. So we're going to try to make this painless. I hate saying just trust me. I don't want to get too deep in the explanations because this video could easily become an hour long, but just kind of trust the process for now. Okay, so definitions. The domain of trigonometric functions refers to the set of all possible input values, which we need to understand in trigonometry. The input values are angles. It's not x, it's not y like it was back in 171. So we're looking for the set of all possible input values, which are angles for theta, for which the function is defined and produces a valid output. Okay? The range of trigonometric functions refers to the set of all possible output values that the function can produce. So back when we were in Math 171, we said, okay, the domain, we already know that that's the input, and we would say, okay, that's X. The range, we would say, okay, well, the range is the output, which is Y. We need to separate ourselves from that thinking when we're talking about the domain and range here, okay? When we're talking about the domain in Math 172, when we're talking about these trig functions, we need to understand that the domain is theta, and the output is some ratio. Okay, so we need to kind of separate ourselves from the idea of domain and range just being x and y, because here, when we're talking very specifically about the unit circle, x and y mean something different. Okay, so we have our definitions. The domain is the set of all possible values for theta that give us a valid output, and then the range is those output values, those ratios. Okay, now we also need to remind ourselves kind of quickly about the unit circle. We've already learned about the unit circle, so we know the unit circle is a circle centered at the origin with a radius of 1. So let's draw that. Pretend it's perfect. My drawing skills lack a lot, but you get the gist, okay? And then imagine drawing some angle, any angle. So we have an angle in standard position. So the origin is the vertex, the positive x-axis is the initial side, and then we can sweep it in the positive counterclockwise direction or the clockwise direction. Doesn't matter. So we just have some arbitrary angle right here. Well, any angle that we draw is going to intersect the unit circle at some point. So this point is just a regular xy coordinate. But we have found that if we can kind of draw these triangles in this unit circle, that those XY coordinates are actually really, really important because with a unit circle, the radius is always 1. And so those ratios are always going to be something over 1. Well, it just so happens that that ordered pair cosine corresponds to the x and sine corresponds to the y. And you can watch previous videos for more information about that. So if we want to review those output values, those ratios for the sine functions, we get that sine is y, the y coordinate of the ordered pair where our terminal side intersects the unit circle. Cosine is x. Tangent we know is sine over cosine, so it's y over x as long as x is not 0. That's important. Cosecant is the reciprocal of sine, so it's always going to be 1 over y unless y is 0. Again, or we don't want y to be 0, so that's important. Secant is the reciprocal of cosine, so it's going to be 1 over x as long as x is not equal to 0. And then cotangent is the reciprocal of tangent, so cotangent is going to be x over y as long as y is not equal to 0. So what we need to do is fill in this table, and we can refer back to this table. Now, I can't say it enough. I hate saying just trust me. I like to explain why, but sometimes if I explain too much, my videos become an hour long and nobody's going to sit and watch that. So for now, trust the process. I'll do a very brief explanation of each of these, and then when we see the actual graphs, we'll kind of revisit this, okay? So what we need to do is remind ourselves what function notation is. So back in Math 171, we would see something like f of x equals something, okay? So we were saying, well, we have f, and this literally reads f of x, But f stands for the function evaluated at some input value x. So we would just say, hey, this really means we're going to take some function f and we're going to evaluate it for some value for x. Well, we can do the same thing in trig, okay? So instead of saying f of x, we want to say f of theta. So theta is our input. So we would say f of theta equals one of our trig functions. So let's look at sine. It's filled into this table. So we have sine. If we want to try this in function notation, we would say f of theta equals sine of theta. We know the output is going to be some ratio, okay? We have that our input is going to be theta, some angle. The output is going to be some ratio, but very specifically for sine, the output is going to be the y-coordinate of the point where the terminal side of our angle intersects the unit circle, okay? Now, when it comes to values for theta, we have no restrictions. Theta can be anything. It can be any positive angle, any negative angle. We could do many, many revolutions around the unit circle. We could literally plug in any value for theta and get some sine ratio. So we would say the domain of sine is all real numbers. Now, when it comes to the range, let's look at the unit circle, okay? Now, we know that the output for sine is the y coordinates of those points on the unit circle. So if we look at the y-axis on the unit circle, we can have at the biggest value for sine could be 1, and the smallest value for sine could be -1. The remaining values for sine are somewhere between -1 and +1. So wherever we end up on that circle, we're never going to be as big as 1. We're never going to be as small as -1. So we would say the output values are all going to be ratios that are between -1 and 1. Okay? And you can see that we've written that range in interval notation. I went brain dead there for a second. Interval notation. Now, unfortunately, this table is one of those that when I try to write on it electronically, things like bounce around and it drives me absolutely bonkers. So you all have this table in front of you in your notes. You can fill it in with paper, pencil. Okay. I'm going to go to a separate document to do this. Okay. So let's see. Let me actually pause the video so I can pull up the other document. Okay, so let me pull up the document that I have that I can fill in. So let's look at cosine, tangent, cosecant, secant, and cotangent. So we're going to go through this fairly quickly, okay? So for cosine, if I wanted to write that in function notation, I would write it as f of theta equals cosine theta. We already know that the input value is going to be some angle. The output is going to be a very specific ratio. And for cosine, the output is the x coordinates of those points on the ordered on the unit circle. Okay. Now, when it comes to the domain, just like with sine, we don't really have any restrictions. We could plug in anything we want. We don't have a ratio where we have to worry about a denominator being 0. We could plug in any positive value for theta, any negative value for theta, tiny values for theta, huge values for theta. The possibilities are endless. So we would say the domain is all real numbers. Now imagine that unit circle. Instead of flipping back and forth, I'm going to draw like a really fake one here. Okay. So we have our unit circle and we have those quadrant angles that happen at 90 degrees, 180 degrees, 270, 360. And we have very specific ordered pairs. So we have 1, 0, we have 0, 1, we have -1, 0, and we have 0, -1. Those points are really important for understanding domain and range. Now, when it comes to the range of cosine, we're looking at the x coordinates of those points around the unit circle. So if we're talking x's, we can never be smaller than -1 on the x-axis, and we can never be bigger than +1 on the x-axis. All of our values for the output for cosine are going to be between -1 and 1. So we would say the range is -1 to 1 inclusive. That means we can include -1 and +1, okay? So it's when we talk about the remaining 4 trig functions that things get weird. And the reason they get weird is because they are all ratios where we have a numerator and a denominator. So we have to be very mindful of when that denominator is 0 for the domain. So let's talk about tangent. So we know that tangent can be written in function notation as f of theta equals tan theta. The input value is some angle theta, and the output value is a very specific ratio. We know that tangent is sine divided by cosine. So if we're talking about points on the unit circle, it would be y over x as long as x is not equal to 0. So when it comes to the domain, we have to actually ask ourselves, okay, well, when is x equal to 0? So when is x equal to 0? Well, x equals 0 here and here. Well, this is pi over 2. This is negative, or this is 3 pi over 2. So we know that pi over 2 and 3 pi over 2 are bad. Okay, so we have issues at pi over 2 and 3 pi over 2. But that's not the whole story. So if I go from, let me do it in a different color. So if I go from pi over 2 and I add pi, I get right back to 3 pi over 2. If I add pi, I get not pi over 2, but 3 pi over 2 plus pi, which is 5 pi over 2. So then if I'm up here at 5 pi over 2 and I go pi radians around the circle again, I end up at 7 pi over 2. And then if I go back around up here, go another pi over, or go another pi radians, I end up at 9 pi over 2. If I go pi radians again, I end up at 11 pi over 2. So we have serious issues at pi over 2, 5 pi over 2, 7 pi over 2, and so on. So when it comes to the domain, we're going to write this very, very informally, and I'll show you a way in another video how to write these formally in set builder notation. But we would just say that the domain is all real numbers except odd multiples of pi over 2. Now, when it comes to the range, this is where I want you to trust me, okay? The range for tangent is weird, and it all comes down to how ratios work. So when you're dealing with fractions, as denominators get bigger, the fraction gets smaller. As denominators get smaller, the fraction actually gets bigger. So when we're dealing with this, we know that we're plugging in values for x, okay, because that's going to be kind of like where the denominator stuff is happening. So as we're plugging in values for x, we know that x is limited because that's cosine, and the range for cosine is -1 to 1. So as we're plugging in those values, -1 to 1, we're getting these values are getting closer and closer to 0. As we get closer and closer to 0, our ratio is getting bigger. So the domain for tangent is all real numbers. And don't get too lost in this. It'll make more sense when you see the actual graph, okay? Now, cosecant, secant, and cotangent are weird too, so let's go through them kind of quickly. So cosecant we can write as a function by saying f of theta equals cosecant of theta. We know the input is theta. The output is a very specific ratio. And we know that cosecant is the reciprocal of sine. Sine is y, so cosecant is 1 over y as long as y is not equal to 0. So then we have to ask ourselves, okay, well, when is y equal to 0? So when is y equal to 0? Well, let's go back up to our really, really, really limited unit circle. Okay, so when is y equal to 0? Let's do that in blue. So y is equal to 0 here and here. So this is at 0 or 2 pi radians. This is at pi radians. Okay, so if I start here at the positive x-axis and I go pi radians, I get an x coordinate or a y coordinate of 0. This is a problem. If I go pi more radians, I end up at 2 pi, where I get y is 0, which is a problem because my denominators can't be 0. If I go pi radians again, I end up at 3 pi, then 4 pi, then 5 pi, then 6 pi, and then 7 pi, and 8 pi. So we could keep going. So we would say we have issues at pi, 2 pi, 3 pi, 4 pi. I could go in the clockwise direction. I would have issues at negative pi, -2 pi, -3 pi. So we would say here that the domain is all real numbers except integer multiples of pi. Okay, and again, we're going to find a fancier way to write that in the next video. Okay, now the range is, again, please just trust me on this. Okay, it is so weird to understand this because you're talking about ratios, and when you're getting closer to 0, your ratio is getting bigger in the positive direction or it's getting further away in the negative direction. So I'm just going to tell you this one, but I promise you it all comes down to ratios. We can talk about it in person, or you can just trust the process, and when you see the graph of cosecant, it'll make more sense. But the range is -infinity to -1, including -1, and then +1 to infinity, including positive 1. Okay, so it's really weird. I promise there's a good mathematical reason for it. It'll make more sense when you see the graph. So next we have secant. So secant we can write as a function as f of theta equals secant of theta. We know the input is theta. The output is a very specific ratio. And because secant is the reciprocal of cosine, it's going to be 1 over cosine, which is x. So 1 over x as long as x is not equal to 0. Okay? So we have to ask ourselves again, when is x 0? Well, we already know this, okay? We already know that x is 0 here. So we would say the domain for secant is the same as the domain for tangent. Okay, we would say it's all real numbers except odd multiples of pi over 2. And the range is the same as cosecant. So again, this all just comes down to this weird kind of understanding of how ratios work and how as denominators get bigger, something happens. As they get smaller, something else happens. Trust the process. So the range here is negative infinity to negative 1, including negative 1. And we union that with 1 to infinity, including the 1. Okay? So hopefully you're filling in your table. We're almost done. So we have next cotangent. So cotangent, we know we can write it as a function by saying f of theta equals cotangent of theta. The input is some value for theta. The output is a very specific ratio. And because cotangent is the reciprocal of tangent, and we know that tangent is sine over cosine or y over x, cotangent is going to be x over y as long as y is not equal to 0. So then we ask ourselves, well, when is y equal to 0? And I'm going to do this in a different color. Well, we can say y is 0. We've already looked at that. Y is 0 at pi, 2 pi, 3 pi, 4 pi, negative 2 pi, negative 3 pi. Okay? So the domain here is going to be exactly the same as cosecant. Okay? So the domain of cotangent is the same as cosecant. So we would say all real numbers except integer multiples of pi. And I'll show you a fancy way to write integer multiples of pi or odd multiples of pi over 2. Now, the range is going to be the same as tangent. So we have this situation where we're plugging in values basically for y. So as y gets smaller, the ratio gets bigger. It's kind of a long process. We could talk about it for a really, really long time. Just know that the domain here is all real numbers. And it'll make sense when you see the graph, okay? So I know it's kind of crappy for me to say, just trust the process and this will make sense later, but just trust the process, this will make sense later. So make sure you fill in your table for the domain and range of cosine, tangent, cosecant, secant, and cotangent. All right.